Okay, this is my first attempt, so let's see. Today we're going to see about derivatives of exponential functions. We already know that the derivative of a variable to a constant is x to the n is n times x to the n minus 1. This is not an exponential function. This is a power function. We also already know that the derivative with respect to x of the natural logarithm of x is 1 over x. So what is the derivative of an exponential function? Well, to find that out, we will need to apply the derivative of the natural logarithm. If we, instead of having just natural logarithm of x, we have natural logarithm of some function of x, then its derivative by the chain rule is 1 over the argument of the natural logarithm, which is f of x, times the derivative of f of x, f prime of x. This is going to be very important. Let's see an example. We have, let's say f of x is 3 to the power of x, an exponential function. Since we don't know how to get its derivative, we're going to take natural logarithm on both sides of the equation, here and here. Applying properties of logarithms to the right side, we get that the x comes down as the in front of the natural logarithm. So we get the natural logarithm of f of x is x natural logarithm of 3. Okay, from here we can differentiate the derivative of the natural logarithm of f of x. We have it here. It's 1 over f times f prime. Now this, the derivative of this is the derivative of x, which is 1, times this constant. Even if it's a natural logarithm, it's still a constant because it's a natural logarithm of a number. So it's 1 times ln of 3. Okay, but what we want is to leave f prime of x by itself. Well, very easy. F of x is dividing here. We multiply times f of x on both sides. And so we get f prime of x equals f of x times natural logarithm of 3. But f of x is 3 to the x. So f prime of x is 3 to the power of x times natural logarithm of 3. And that's our answer. Now let's see if I can take this off and see another example. Oh yes. Okay. We'll have this function, which is by far more complicated than our previous 3 to the power of x. G of x is 3x to the 5th plus 2 quantity to the 10x cubed. It is an exponential function. We have a variable in the exponent. So again, we take natural logarithm on both sides of the equation. And on the right side, we apply properties of logarithms. Basically, taking this exponent and moving it in front. So we get this. 10x cubed, natural logarithm of 3x to the 5th plus 2. Then we get the derivative. Derivative of the natural logarithm of g, 1 over g times g prime of x. And now we have a product here. A product. So it's the derivative of the first function, 30x squared, times the second, here, plus the first function, 10x cubed, times the derivative of this natural logarithm, which is 1 over 3x to the 5th plus 2, times the derivative of this, which is 15x squared. Then we try to simplify. the only thing that can simplify here is this 10x cubed times 15x squared, which is 150x to the fifth. So we get the same 30x squared, natural logarithm of 3x to the fifth plus 2, plus 150x to the fifth over 3x to the fifth plus 2. But what we want is g prime by itself, so g multiplies on the other side. Here we go. It's just g of x times this sum. And instead of g of x, we of course write what g of x is. So we have g prime of x is 30x to the fifth plus 2 quantity to the power of 10x cubed times 30x squared natural logarithm of 3x to the fifth plus 2 plus 150x to the fifth over 3x to the fifth plus 2. And that's our answer. Let's see another one. Okay, this. Okay, good. Okay, let's take the function j of x is sine of x to the power of cosine of x. Again, we have variable exponent. So we take natural logarithm on both sides. Here we go. Natural logarithm, natural logarithm. On the right side, we apply properties of exponents. Cosine goes here. So we have cosine of x, natural logarithm of the sine of x. The derivative of natural logarithm of j of x is 1 over j times j prime. The derivative of this product again, the derivative of cosine, negative sine, times natural logarithm of sine, plus the first function, cosine, times the derivative of the natural logarithm, which is 1 over sine times cosine. Simplifying this, we have a cosine and another cosine, so it's cosine squared of x over sine of x. And again, that's 1 over j times j prime, but we want j prime by itself. So j multiplies, here's j, times this big expression. And that's the answer. Yeah, some of you might say, well, do we really want the fraction with sine and cosine? And you might be, you're right. Sometimes you don't want the fraction. But so we can take this expression, cosine over sine, and that is cotangent. Cosine over sine is cotangent. So instead of writing cosine squared over sine, here's the two cosines and the sine, we can combine these two and say this is cotangent. So cosine times cotangent, which is what I wrote here. Either answer is correct. Let's see one last occasion when we use this. Sometimes we have a big product or a big quotient. This is an example of a product. Got the function y equals 5x plus 2 to the 8th power times 8x minus 1 to the 5th power. To get the derivative, before we used simply the product rule, and then we had to find a common factor and all that. We can also use logarithmic differentiation, what we've been doing. Take the logarithm on both sides. We put natural logarithm here and natural logarithm here. Here we apply properties of logarithms. We have a product, so it's the natural logarithm of the first factor plus the natural logarithm of the second factor. More properties of logarithms. The 8, that's an exponent on the argument, can go in front. the same as this 5. That's what we have here. Okay, once we have it all nice and neat and linear in terms of logarithm, we can take the derivative. The derivative of ln of y is 1 over y prime. 8 times ln of 5x plus 2, its derivative is 8 times 1 over 5x plus 2 times the derivative of 5x plus 2, which is 5. Same thing happens here. We have 5. The derivative of ln of 8x plus 1 is 1 over 8x plus 1 times the derivative of 8x plus 1, which is 8. Simplifying here, it's 8 times 5 times 1 is 40. 5 times 1 times 8 is 40. So we have that. To leave y prime by itself, y multiplies times the whole thing. So we have y times this expression. And y is, of course, this. The same as the original, the part in purple. Now, if you do not, you can leave the answer like this. However, if you do not want fractions with so big factors, now it's very easy to distribute. Let's see. If we distribute this over this fraction, basically one of the 5x plus 2 cancels. Okay, so we could have 5x plus 2 to the power of 7 times 8x minus 1 to the power of 5 times 40, I guess I missed the 40, plus, again, the other 40 times 5x plus 2 to the power of 8, and one of the 8x minus 1 cancels. So that would be 8x minus 1 to the power of 4. And that's another answer. And of course you can still get a common factor. Okay?